All right, today we're going to be looking at section 2.3. These are techniques for computing limits. And we start out with a example and definitions. So the limit of a linear function is just a straight line. We are given that since it is a straight line, we can find the limit by just using direct substitution. And so it leads to a theorem. If you have a, b, and m that are real numbers, for the linear function f of x is equal to mx plus b, the limit of f of x, so some linear function, as x gets closer and closer to some a value, is the same as just plugging in that a value to the function, which is plugging it into the linear function. So as you get closer to some x value, your function is getting closer to the y value when that function is evaluated. And then you see a few examples where they explain it and show it as you plug it in. This eventually leads us to some limit laws. So there are several rules and laws that we can use. So it says assume that f of x as x gets close to a and g of x as x gets close to a exists. So you are evaluating the limit from left and right side, and both of them exist. Where c is a real number and it says n is greater than 0, that's a real integer, we get these following laws. So the limit of a sum, so you're taking the limit but you're adding two functions. The limit of the sum is equal to the sum of the limits if you separate them. Okay? If you take the limit and you evaluate the difference, so the limit of a difference is equal to the difference of the limit. So you find the limit of each individually and subtract them. You can multiply a limit by a constant, okay, and that's the same thing as evaluating the limit and then multiplying by that constant. You have the product rule. So the limit of the product is equal to the product of those two limits. You have a quotient rule. Okay, the limit of a quotient is the quotient of the limits provided that the denominator, in this case g of x, is not equal to 0. You have a power rule. So if you evaluate a limit and raise it to a power, it's the same thing as the power of the limit. And then if you have a root, so this says is even. Okay, so this lets you know this is even. So we're saying this is an even root, 2, 4, 6, 8, something that is even. And you will have a result provided that your argument, whatever is under the root, is greater than 0, because we cannot take the root of negative numbers, not an even root. So these laws apply when evaluating limits, and then you go through a series of examples and they show you kind of step by step how some of this works. And then we start going into polynomial and rational functions. So as we're evaluating the limit of polynomials, some of the same can be done by plugging in an exact value. So this is again direct substitution. You're getting close to some x value, you can plug it in and we will get a result, again provided, if we're doing a rational function, provided that the denominator is not equal to 0. So just keep remembering that. So then you have this theorem. You got polynomial functions. The limit of some polynomial function as x gets close to a is going to be equal to the p of a value, direct substitution. With rational functions, same thing, limit of p of x divided by q of x as x gets close to a is going to be equal to the value directly substituted in, again provided that the denominator is not equal to 0. And then of course we show you an example with the textbook, so very good to read over and kind of understand what's going on here. Then we remind you of left and right sided limits, so one-sided limits. So the limit laws for one-sided limits. So when you're doing a root, we're looking at left and right side because we have to have an integer when we're doing roots. So it says laws 1 through 6 hold with limits replaced with the limit from the left or the right side, and it's modified by the following. So the limit of f of x raised to the 1 over n power, so some root, as x gets close to a from the right, so we're coming from the right going to the left, is equal to, again, this limit, provided that our argument is positive, so greater than or equal to 0 for all x near a, with x being greater than a if n is even. So this has to be an even integer. Got to remember that. This doesn't work for like a 1/3, 1/5 power. And then the same thing for the left-sided limit, provided your argument is greater than 0 and that n is even. So then they show you an example here. Got a square root, even root. They go through and walk you through each of the steps, and you can kind of see the graph here. Then we have a few other techniques. Sometimes it says we cannot find the limit by using direct substitution. So like we just plug in a number, maybe it doesn't exist, maybe there's a hole in the graph, and so we have to apply some other techniques to find the limits. And here we start applying, it says it down below. So we use some algebraic techniques where we have to factor and cancel out in this example. And then we can able to get an answer. Sometimes we might have to multiply by the conjugate to cancel out the square root. And then you can simplify some algebraic and find the limit. And then some more important limits. We start doing some trig. This is actually exponential. We'll have a little bit of both of them. So trying to find the limit when we have an exponential, again, sometimes may be hard. So we approach this one numerically, making a table coming from the left and right, using the same concept that we did in 2.1, which finding the slope of the secant lines and seeing how that approaches the slope of the tangent line, numerically from the left and the right. And then we come upon another theorem, which is going to be the squeeze theorem. Squeeze theorem just says sometimes it's hard to compute a limit algebraically or direct substitution. So one thing we do is we find a function that is greater than and a function that is less than, and we squeeze our function between it. So that function is kind of trapped in between two functions. And so the definition says, assume we have functions f, g, and h, and they satisfy the condition that f is less than g and g is less than h. So g is the one in the middle. And this is true for all x values near a specific value a, except maybe at a. So all of them, f is going to be less than, h is going to be greater than, everywhere except for maybe at one point. It says if the limit of f of x as x goes to a is equal to the limit of h of x as x goes to a, so the least function and the greatest function are equal to each other as we get close to a, then consequently g, the function that is trapped in between them, also has to have a limit of L as x gets close to a. And then so you see an example of applying the squeeze theorem, and this is applying a trig function between two polynomial functions. And then we start talking about the trigonometric limits and applying the squeeze theorem to those as well to show you how we arrive at the results because the trig functions are oscillating, and so we kind of trap it between 2 points and apply the squeeze theorem. And then we also have some trigonometric limits when the denominator is 0 and you cannot evaluate it, so we have to use some other methods. Again, it says direct substitution does not work because the denominator is at 0. So once you plug in that value, you get 0. So we got to kind of use some manipulation to solve it. So here they're using Pythagorean identity to rewrite one of the functions, and then use some algebra to simplify, cancel out some terms, and then you substitute in once you kind of get rid of some of that problem, and then you can evaluate the limit. So you got some examples there. So overall, there's a lot of theorems that we're kind of seeing when evaluating limits. So we got the laws for applying linear, polynomial. We also have some exponential functions where we start using the squeeze theorem, and some trigonometric functions, which we call transcendental functions. So do read over these, look at the examples. With this, we're going to go ahead and jump into MyMathLab and begin working some of those examples.